In the first part of our course, we are going to discuss something called operational amplifiers. Operational amplifiers are differential amplifiers. They were part of the circuits course like few years ago, and the electronics group decided to move it to the electronics course. So it's basically circuit analysis. There are no much electronics there, but it's about circuit analysis of the operational amplifier. The operational amplifier is like an amplifier. It's a big circuit that contains transistors, capacitors, resistors. It's a very, very big circuit. However, we are not going to go into the details of the circuit. We are going to study the amplifier as a block. Okay? So we are going to do circuit analysis for the amplifier, as you will see. The outline of the chapter here, or the slides that we are going to study. First, we are going to identify or introduce the terminals, the different terminals of the operational amplifier. By the way, we call it the op-amp as an abbreviation. Okay? We are going to introduce the different terminals, the different voltages and currents, and then we are going to mainly focus on ideal op-amp, the ideal op-amp characteristics, what kind of ideal characteristics are there, how we use these characteristics to solve the circuits that contain ideal op-amp. And then we are going to talk about some applications for the op-amp, for example, the inverting amplifier, summing amplifier, non-inverting amplifier, difference amplifier, and at the end there will be something called the instrumentation amplifier, which is an extension of the difference amplifier. The op-amp will deal, as I said, will deal with it as a block. We are not going to go into the details of the circuit. So the op-amp will be represented by this triangle. Okay? Inside this triangle, there is a big circuit, as I explained. It contains transistors, it contains resistors, capacitors, many elements inside this block. However, we are not going to focus on the details of the op-amp. We are going to deal with it as a block with some input terminals and output terminals and DC bias. So the most important terminals that we are going to use for the op-amp are, we have two input terminals, one terminal with a negative sign called the inverting input, the other terminal is called the non-inverting input with a positive sign. And then we have the output taken from here, and then any amplifier that we'll deal with in our course or later in any other course, you will see that any amplifier needs DC sources. You need a positive DC source and a negative DC source in order for the amplifier to work properly. And this will be explained later when we study the amplifiers and the transistors in our course. But an amplifier cannot work without a DC bias, a DC source, positive and negative, or positive and ground. So at least you need a positive DC source, okay? So here in the op-amp, we usually connect positive DC source and negative DC source to bias the amplifier. Usually they are equal. However, sometimes you can make them unequal. So you can use positive 15, for example, for the DC, for the positive DC bias, and negative 10 for the negative DC bias. But usually they are equal. Okay. So these are 5 important terminals for our operational amplifier. Okay. However, in practice, operational amplifier, in practice it looks like this. It's a black chip. If you go to the lab, you'll find that operational amplifier, it looks like a black chip, okay, with 8 terminals. 5 of them we explained. 5 of them are the 2 inputs, the 2 bias voltages, and the out. What about the other 3? The other 3 we don't use. 2 of them are called offset null, and we use in practice in order to treat the offset that comes from any mismatch inside the op-amp. When the op-amp is not well manufactured, if there is a mismatch between the components inside the circuit of the operational amplifier itself, it may lead that the voltage, instead of being, for example, 0, it will shift. There will be an offset in the voltage. In order to treat this offset, they use these terminals, offset null and offset null, in order to shift the offset up or down to treat this offset, okay? And the 8th terminal, it's not connected, doesn't connect to anything. It has no use, it's not connected to anything. So for our course, for the purpose of our course, we have only 5 useful terminals. Although in practice you have 8 terminals, but 5 of them are important to us. the inverting input, the non-inverting input, and these are two inputs, okay? Why do we have two inputs in an amplifier? Because the op-amp, originally it's a differential amplifier. What does it mean, differential amplifier? It amplifies the difference between two inputs. This is the meaning of a differential amplifier. It amplifies the difference between two inputs. That's why we have two inputs here, one output, and as I explained, we have a positive DC bias and a negative DC bias. This is how we connect the amplifier. This is the conventional voltages and conventional currents. So we usually call the non-inverting input, we call the voltage across between the non-inverting input and the ground, we call it VP from V positive. We call the voltage between the inverting input and the ground Vn in this direction, negative, positive, negative, positive. So these are the conventional directions, okay? The DC bias, we usually connect a positive DC bias here with a positive battery, negative DC bias here with a negative battery, and this is the output, V output between this terminal and the ground. Okay, for the currents, the default is, if I tell you IP is the current going to the non-inverting input, it's in this direction. IN by default, it's the current going into, that's why we say these are the conventional directions, into the inverting input. I output is the current going into the output terminal. IC plus, which is the current of the DC, positive DC supply going into the amplifier, and IC negative is also the current going into the amplifier. So all the currents, the conventional directions for all the currents are going into the op-amp. So these are the conventional directions for the voltages and for the currents. In some textbooks, they name these voltages with other names. For example, in some textbooks, you might see that this voltage is called Vx, this voltage is called Vy. In some other textbooks, they call this voltage of the non-inverting, they call it V1, and the other one is V2. Okay, so there are different names. It doesn't matter for us. The naming doesn't matter. You need to understand how to deal with these voltages regardless of their names. However, for simplicity, I choose that VP, just to remember that this is positive. This is of the non-inverting term input, and Vn that comes from negative. This is for the inverting input. So these are the conventional voltages and currents. The characteristics of the amplifier, the transfer function of the amplifier, which is the relation, transfer function means the relation between the input and the output. They look like this. This is the transfer function of the op-amp. The vertical axis is the output, and the horizontal axis is the difference between the non-inverting input and the inverting input, Vp minus Vn. So the horizontal axis is the difference between the two inputs, and the vertical axis is the output. You see that there is a linear relation here between the output and the input. And this linear relation or line, it has a slope. The slope of this line represents something called the open loop gain. What does it mean, gain? Gain means V output over V input. How much you amplify the input. This is the meaning of a gain. So the gain A is V output over V input. But V input here, our input is not one input, it's the difference between the two inputs, right? Between the non-inverting input and the inverting input. So this is called the open loop gain. It's the amplification factor. How much the output was amplified with respect to the difference between the two inputs. This is called open loop gain. What is the meaning of open loop? Open loop means this is the gain of the op-amp itself. This is the gain of the op-amp without connecting it to any other circuit elements. That's why we call it open loop. So the op-amp itself, it has a gain A without connecting it to any other circuit elements. So if you take V output here and you divide it over Vp minus Vn, you will find that the gain is called A. This is called open loop gain. So the word open loop means it's the gain of the op-amp alone without connecting it to any circuit elements. Later, we'll see that when you connect the op-amp to some circuit elements like resistors, there will be another gain called G, closed loop gain. G, the closed loop gain, is the gain of the op-amp circuit when you connect it to some other circuit elements. Okay, so this is the difference between open loop and closed loop. Anyways, so here in the middle, in this part, there is a linear relation between the output and the input, and there is a gain. There is a gain, and the gain equals to the slope. Why the gain is equal to the slope? Because in this region, if you have a relation that looks like a line like this, this is Vp minus Vn, and this is V output. What is the slope of this line? What's the slope of this line, guys? Huh? The slope is delta y over delta x, right? The slope of a line is the change. Slope is the change in the vertical x over the change in the horizontal x. Like the change in the vertical x over the change in the horizontal x, this is the ratio between the output and the input, right? This is the ratio between the output and the input. That's why the slope of this line is equal to the gain A. So here the slope of this line equals to the gain. What happens next? Once you reach to a certain point here, at which the output reaches the positive DC supply, the positive DC bias. You remember we said that any amplifier needs a positive DC supply and a negative DC supply, right? The importance of DC supplies, of these DC supplies, is that the output voltage cannot exceed, the output voltage of the amplifier cannot go above the positive DC supply, and it cannot go below the negative DC supply. So once the output reaches the positive DC supply, it will saturate. It will say, no, I cannot increase more than that. And then the gain here will be zero. The slope of the line will be zero, right? So here, starting from here, we call this region saturation. We call this region the linear region. Here we call it positive saturation. On the other hand, when the output reaches negative VCC, the negative DC supply, the negative DC bias, it will say no, I cannot go below that level. Then it will saturate again, and the gain becomes zero. We call this region negative saturation. So this is the transfer function of the op-amp. It has three regions. Linear region, this is the most important region to us. I will explain why in a few minutes. Okay? Then positive saturation, when the amplifier saturates, and the negative saturation. In the positive saturation, negative saturation, the gain is zero, which means what? The gain is zero means that the output will not change. Even if you increase the input, the output is constant. It doesn't change. So the gain here is called zero. It's zero, right? Whatever the value of the input, the output will not change. It will be constant, it will not increase. If you increase the input, the output doesn't increase, so the gain is zero. Same here for the negative saturation and positive saturation. While here in the linear region, if you increase the input, the output increases. You increase the input more, the output increases. Okay, why the linear region is very important to us? Because any amplifier that we design in our life as an engineer, okay, must be linear as much as possible. Why? Because linearity guarantees that the output will be the same as the input but multiplied by a constant. So if the input is sine omega t, then the output will be constant multiplied by sine omega t. So here linearity guarantees that the output will be the same waveform of the input but amplified, multiplied by a constant, which is the gain, right? But if you have some region that is not linear, whether it's saturation like this or quadratic or anything that is not linear, you will find that the output will be distorted. So here, this is under the linearity. Under the linearity, the output will be constant multiplied by the input. But under saturation, for example, if the saturation happens, what happens to the output? The output will be constant, VCC. So you input sine and you get constant. Is that an amplification? No, this is not an amplification. So for example, imagine that you want to amplify your voice. You want to amplify Quran sound, for example, or a song. You want the song to be exactly the same, but multiplied by bigger gain, right? But assume that I give you a song to amplify, and then you give me a DC voltage, constant, T, nothing, right? So this is not called amplification. So an amplifier, in order to work properly, for an amplifier to work properly, you need to operate it in the linear region. Otherwise, it's not called an amplifier. It will not amplify. It will give you a constant. So here, that's why the linear region is very important. Let's here see, since the gain here, since the slope of this line is A, then this point at which, for the input at which the amplifier is going to saturate will be the positive DC voltage divided by A. This point at which the amplifier is going to saturate in the negative side will be the negative DC bias divided by A. Here, the positive DC bias and the negative DC bias, they have the same magnitude, but it's not necessarily. Maybe, as I said, maybe in some applications, this will be 15 and this will be negative 10. So here you divide the positive DC voltage divided by A, and here you divide the negative DC voltage by A. Okay? So you can write this relation mathematically, that the output equals the gain multiplied by the input in the region in the middle, for this region in the middle, and then after this it will be negative VCC, and from the other side it will be positive VCC. Okay? So this is how mathematically you can write this relation. When the gain multiplied by the input tries to be above VCC, then the output is going to saturate at VCC. When the gain multiplied by the input tries to be less than negative VCC, the output is going to saturate at negative VCC. In the region in between, when the gain multiplied by the input is between VCC and negative VCC, between this level and this level, when the output is between VCC and negative VCC, it will be a linear relation between the output and the input. Okay, we'll stop here in this video and we'll continue in the next video, inshallah.